Chapter 12 covers solutions. Now, when we think of a solution, what your mind probably goes to first is something like an ionic solution, so a solid dissolved in a liquid. But solutions can be any phase dissolved in each other. So, for example, it could be, you can think of air as a solution, as a gas dissolved in a gas. Gases can be dissolved in liquids, like in pop or club soda. A gas can be dissolved into a solid. The example there is a catalytic converter in your car is carbon monoxide infused in platinum. Liquid can be dissolved in a gas. So here, solvent is simply the major component and solute is the minor component. So liquid dissolved in gas would be water vapor and air. Liquid in a liquid could be something like vodka, ethyl alcohol dissolved in water. Liquid in a solid is, an example is dental amalgams used to fill cavities. A solid in a gas, naphthalene, which is mothballs, can go into the air, but it's still a solid particle. A solid in a liquid, seawater, that's the one that you most commonly think of. And then a solid in a solid would be other brass or alloys. Brass is zinc in copper. So here's a picture of a gas dissolved in a liquid. So carbonation is carbon dioxide gas dissolved in the liquid, and then when the pressure is released, the gas goes from the aqueous phase into the gas phase. Solubility is when one substance, the solute, dissolves in another substance, the solvent. When that doesn't happen, it's said to be insoluble. So an example is oil is insoluble in water. Back in Chem 103, we talked about a variety of insoluble salts that don't dissolve. Now, solubility is going to depend on two factors. The first is nature's tendency towards mixing, which we will talk about more in depth, and then about the types of intermolecular attractive forces in between the substances we're talking about. So that nature's tendency towards mixing is called entropy. And most processes occur because the end result has less potential energy. So there's some sort of difference in potential energy. But if we're looking at say, mixing these two gases together, neon and argon, there's no change in potential energy there when they mix. But you know from experience that if you get rid of this divider, the two gases are going to mix together. So the difference in attractive forces is negligible. There's no difference in potential energy. But the reason they mix is because of entropy, nature's tendency towards mixing, towards disorder, and that lowers the energy of the system. We can also talk about intermolecular forces. The energy change is going to involve some sort of difference between intermolecular forces. Most of the time, the noble gases mixing is kind of the exception to that. So, in order to mix solvent and solute together, you have to break all of the solute attractive forces. If it's, say, a solid, you have to break all of these atoms or molecules apart. You have to break some of the solvent attractive forces, and both of those are going to be endothermic. You're breaking intermolecular forces. That's going to cost some energy. But you're also going to gain some energy from new solute-solvent attractions, which is an exothermic process. So whether forming a solution is endothermic or exothermic is going to depend on the balance between these new forces formed and what it costs to break the old ones. Just a quick reminder of intermolecular forces. Everything has dispersion forces. Dipole-dipoles are found in polar compounds, and then hydrogen bond is a special form of dipole-dipole where you have a hydrogen bound to either an oxygen, a nitrogen, or a fluorine. And then ion dipole occurs between a polar molecule and a ion, so a positive or negatively charged ion. So the way to tell if a solution is going to form when we're looking at intermolecular forces, if those new solute to solvent forces are greater than the solute to solute ones that you're breaking, and the solvent to solvent ones you're breaking, then the solution will form. If they're equal to each other, the solution will form. But if that solute to solvent is lower than the ones that you have to break, the solution may or may not form. And if it does form, it's going to be endothermic. The general rule for if a solution will form is that like dissolves like. So things with similar intermolecular forces will form solutions. There are a variety of solvents we use in chemistry. This is not an exhaustive list, but it will show you at least some of them. So water is what we're going to generally use in this course. And then as you go down, methyl alcohol, ethyl alcohol, acetone, toluene, hexane, diethyl ether, carbon tetrachloride. Those are all more commonly used in the organic lab, although once in a while you will run into them in general chemistry as well. Notice we have some polar molecules and some nonpolar molecules for solvents. All right, let's review our intermolecular forces and apply it to things being soluble. So predict whether the following vitamin C here, is soluble in fat or water. So fat is going to be nonpolar, water is polar, and has H bonds. So if we look at our vitamin C here, we can see that there are a lot of OH groups that can hydrogen bond, plus a couple other oxygens that will make it polar and can be hydrogen bond acceptors. And so vitamin C is going to be more soluble in water. What about vitamin K3? If you look here, there are two oxygens. Neither of them has a hydrogen on it, so they can be hydrogen bond acceptors, but they're not good donors. And there are a lot of carbons there. And so those two oxygens are not enough to overcome all the carbons. And so this one is going to be a fat-soluble vitamin. Oh, they're also pulling in equal and opposite directions, making it nonpolar overall. Couple more examples to think through. Vitamin A and vitamin B5. Vitamin A is fat soluble because of all of those carbons. There's only one OH group and a lot of carbons. Vitamin B5, we have multiple OH groups and a couple of oxygens, and so this one is going to be water soluble. One more example. Decide if the following are more soluble in hexane. Hexane is C6H14. It's nonpolar or water. So take a look, make your predictions. Naphthalene is all carbons and hydrogens, so it's going to be more soluble in hexane. Formaldehyde is polar, and so it's going to be more soluble in water. And then stearic acid here, it does have a carboxylic acid here at the end, but there's a whole bunch of carbons. Generally, one oxygen can pull 4 carbons with it. And so you can see there are far more carbons than that little group can pull. And so that's going to be more soluble in hexane.